For nearly a century, we've told ourselves a story about the origin of our universe, a tale of an immense explosion, a Big Bang that birthed everything we know from an infinitely hot, infinitely dense point smaller than an atom. This cosmic Genesis story has been our best explanation for how our universe came to be. It's the cornerstone of modern cosmology, the foundation upon which generations of astronomers and physicists have built their understanding of reality itself. But what if this story, this narrative we've clung to, is fundamentally incomplete? Or worse, what if key aspects of it are simply wrong? In 1929, Edwin Hubble made an observation that would forever change our understanding of the cosmos. By studying distant galaxies, he discovered something remarkable. They were all moving away from us, and the farther away they were, the faster they seemed to be receding. This led to a profound realization. The universe is expanding. Wind the cosmic clock backward, and everything converges to a single point. The Big Bang Theory was born, an elegant explanation that seemed to answer that most fundamental question: where did everything come from? But science is never settled. It's a continuous journey of questioning, challenging, and refining our understanding. And in recent years, startling new evidence has emerged that's forcing cosmologists to reconsider some of their most basic assumptions about the Big Bang. These aren't minor tweaks or adjustments to the theory. They represent potentially paradigm-shifting revelations about the nature of cosmic origins. So, are you curious to see what they've learned? What evidence has come to light that's causing such a stir within the scientific community? I'm Alex, and you're watching Space Truths. Today, we're exploring the emerging evidence that's challenging our traditional understanding of the Big Bang, from quantum gravity to cosmic inflation, and what these new insights might tell us about the true nature of our universe's beginning. It's one of life's little ironies that it's not new, cutting-edge technology that is advancing our understanding, most in this field, but rather a return to the fundamentals of physics with fresh perspectives. The standard Big Bang model has always had its gaps and inconsistencies, problems that scientists have acknowledged but often overlooked in favor of the theory's impressive explanatory power. But now, these gaps are becoming impossible to ignore. Let's start with one of the most consequential issues, the singularity problem. The mathematics of general relativity, Einstein's masterful description of gravity, predicts that at the moment of the Big Bang, the entire universe was compressed into a point of infinite density and temperature. This is what we call a singularity, and it's where the physics we understand breaks down completely. Temperature, density, space, and time lose all meaning at this point. But singularities are problematic. They're mathematical anomalies where our equations can no longer describe reality. When I look back, I realize how little we actually knew about cosmic origins before quantum gravity, says theoretical physicist Gabriela Mendez. We were describing the universe back to a trillionth of a second after the Big Bang, but couldn't penetrate that crucial moment of creation itself. We discovered there were gaps we didn't know were there to be discovered. Time after time. The singularity problem hints at something fundamental. General relativity, which describes gravity on cosmic scales, and quantum mechanics, which governs the subatomic realm, are incompatible at the extreme conditions of the early universe. They're speaking different mathematical languages, and their conversation breaks down precisely where we need it most, at the beginning of everything. But what if the Big Bang wasn't actually the beginning? What if our universe didn't emerge from a singularity at all? This is where things get truly mind-bending. Recent theoretical work in quantum gravity, particularly string theory and loop quantum cosmology, suggests something revolutionary: that the Big Bang might have been more of a big bounce, The Big Bounce theory proposes that our universe didn't begin from a singularity, but rather expanded from a previous contracting phase. Imagine a universe that contracts until it reaches a minimum size, not a singularity, but a quantum mechanical lower bound, and then bounces back into expansion. This would mean our universe has potentially gone through countless cycles of expansion and contraction, with no true beginning at all. This might sound like science fiction, but the mathematics supporting this model is rigorous and increasingly compelling. Loop quantum cosmology, for instance, applies the principles of quantum mechanics to space-time itself, treating it as discrete, rather than continuous, more like a fabric woven from fundamental threads than an infinitely divisible sheet. And when these equations are applied to the early universe, the singularity vanishes, replaced by a quantum bounce. Take a look at this simulation. It shows the universe's volume over time according to both traditional Big Bang cosmology and loop quantum cosmology. Notice how in the standard model, volume reaches zero. That's the singularity. But in the quantum model, it reaches a minimum and then rebounds. This isn't just a mathematical trick. It's a fundamentally different understanding of cosmic origins. But the bouncing universe is just one challenge to conventional Big Bang theory. Another comes from cosmic inflation, the theory that the universe underwent an exponential expansion in the first fraction of a second after the Big Bang. While inflation elegantly solves several problems with the standard model, it raises as many questions as it answers. For one, what triggered inflation, and what caused it to stop? The standard explanation invokes a hypothetical inflaton field and its associated particle, but neither has been directly observed. Recent precise measurements of cosmic microwave background radiation, the afterglow of the Big Bang, from the Planck satellite have revealed patterns that don't perfectly match the predictions of the simplest inflation models. These discrepancies might seem trivial, but in science, it's often the small anomalies that lead to revolutionary discoveries. Remember when Mercury's orbit didn't quite match Newtonian physics? That tiny discrepancy eventually led to Einstein's theory of general relativity, which completely transformed our understanding of gravity. Another challenge comes from the cosmos at its largest scales. When we map the distribution of galaxies, in the universe, we find enormous structures, galaxy filaments and supervoids stretching across billions of light-years. Some of these, like the Boötes void, an enormous bubble of emptiness, 330 million light-years across, are so large that standard Big Bang cosmology struggles to explain how they could have formed in the time since the universe began. The immense size of these structures suggests either that the universe is older than we think, or that something in the early universe created density fluctuations on scales larger than inflation should allow. Either way, it points to gaps in our understanding. And then there's the dark sector, dark matter and dark energy, which together make up about 95% of the energy content of our universe, yet remain profoundly mysterious. The standard Big Bang model doesn't explain what these substances are or why they exist in the proportions we observe. It simply incorporates them as necessary components to make the equations work with our observations. This is particularly problematic for dark energy, which appears to be driving the accelerated expansion of the universe against the pull of gravity. Its density seems fine-tuned to an absurd degree, just enough to allow galaxies and stars to form before driving an eternal cosmic expansion. Change its value even slightly, and the universe either collapses immediately or expands so rapidly that no structure ever forms. Then there's the matter-antimatter asymmetry problem. The laws of physics suggest that the Big Bang should have produced equal amounts of matter and antimatter. Yet our universe is overwhelmingly composed of matter. Where did all the antimatter go? The standard model has patch solutions for this, involving subtle differences in how certain particles decay, but these haven't been conclusively demonstrated. Scientists once believed that these problems would destroy any coherent theory of cosmic origins. However, pioneer theories like eternal inflation, the ekpyrotic universe, and string gas cosmology had previously been able to address some of these issues, which emboldened cosmologists to pursue even more ambitious models. But failure would mean disaster for our fundamental understanding of reality itself. Luckily, a new generation of theories is emerging that might offer more comprehensive solutions. One intriguing alternative, developed by theoretical physicist Sean Carroll and colleagues, suggests that the Big Bang might have been more of a big change, a transition from one phase of the universe to another, similar to how water can transition from ice to liquid. In this scenario, the universe didn't begin 13.8 billion years ago. It merely transformed from a state with different physical properties. Another radical possibility comes from string theory and the concept of the multiverse. Perhaps our universe is just one of many, a bubble in a vast, eternally inflating sea of universes, each with different physical laws. In this picture, the Big Bang wasn't the beginning of everything, just the birth of our particular cosmic bubble. But how can we possibly test these esoteric theories? After all, we can't travel back to the beginning of time or observe other universes. This is where cutting-edge observations come in. The James Webb Space Telescope is peering further back in cosmic time than ever before, studying the first galaxies that formed after the Big Bang. These observations are already raising eyebrows. Many of these early galaxies appear larger and more structured than standard cosmology would predict. Meanwhile, gravitational wave observatories like LIGO and Virgo are opening an entirely new window into the cosmos. They've already detected ripples in space-time from colliding black holes and neutron stars, but future, more sensitive detectors might detect primordial gravitational waves, echoes from the earliest moments of the universe that could distinguish between competing cosmological models. Even with all these advances, and with the probes performing far better than their engineers could possibly have hoped for, we must acknowledge the profound limitations of human knowledge. What would happen if we could somehow observe the exact moment of cosmic origins? Would our theories hold up, or would we encounter something entirely unexpected? NASA scientists are designing multiple experiments to test various aspects of these theories, yet the ultimate answers may still elude us. Each of these theories, the Big Bounce, eternal inflation, the ekpyrotic universe, has its strengths and weaknesses. None perfectly explains all observations without introducing new puzzles. But this is exactly how science progresses. Old models are challenged, refined, or sometimes replaced entirely when new evidence demands it. The beauty of this scientific revolution is that it doesn't diminish the achievements of the standard Big Bang theory. For decades, it has provided our best framework for understanding cosmic evolution, successfully explaining the expansion of the universe, the abundance of light elements, and the cosmic microwave background. What's happening now is an evolution in our thinking, building upon what works while addressing what doesn't. Our understanding of cosmic origins will likely look very different in a decade, says cosmologist Carlos Frank. We're not throwing out the Big Bang entirely, but rather refining it, addressing its flaws, and extending it into realms where it previously couldn't reach. For the non-scientist, these debates might seem academic. Does it really matter whether the universe began from a singularity or a bounce, or whether it's part of a multiverse? But these questions touch on something fundamentally human: our desire to understand where we came from. The story of cosmic origins is, in a very real sense, our origin story. When we look up at the night sky, we're looking back in time, tracing our lineage to the stars. The fact that we, collections of atoms that gained consciousness, can even contemplate these questions is nothing short of miraculous. We are the universe becoming aware of itself, using the laws of physics to understand its own creation. There's a profound poetry in that, regardless of which cosmological model ultimately proves most accurate. So, as we reconsider the Big Bang, we're not simply revising a scientific theory, we're rewriting our cosmic autobiography. And in that process, we're reminded of how much remains unknown, how the universe still holds secrets that our most brilliant minds are only beginning to unravel. The cosmos is vast beyond comprehension, ancient beyond imagination, and more complex than our theories can fully capture. Yet we persist in our quest to understand, driven by that uniquely human blend of curiosity and wonder. Whether through quantum gravity, multiverses, or ideas not yet conceived, we continue to refine our cosmic origin story. One observation, one equation, one insight at a time. Thanks for watching. I was honestly blown away by all the incredibly kind comments and messages you've sent me about our previous explorations of cosmic mysteries. If you haven't joined the Patreon party yet, we're still on our long-term 1,000 Patreon member drive, so you can go to the link in the pinned comment to become a part of that effort. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Space Truths content. I'll see you next time.